Professor.
Hello, how you doing?
Good, how are you?
All right.
Were
How can I help
you
you?
were you able to look at that problem that I sent you?
Yeah, I replied either last night or this morning. I can't remember
Yeah,
what.
you did. I got your response, but like was it the
Yeah, it's weird. I think what they did is I think they were originally calculating the electric field, and they changed the question to be calculating the energy stored in the electric field because the answer they gave you is exactly one half of the electric field strength. Uh, that you'd calculate if you try to do that. So the answer they were expecting you to put was that 1.7 times 10 to the seventh joules per square meter. But of course, the units aren't in volts per meter, which is what electric field would be. So I've just had to throw that question out. I might remake it later to make it more useful and correct, but right now I've just taken it out so we won't get it in future tests anyways. I can't take it out of the test that exists, but yeah. So you did everything right. It's just a matter of it was a
oh,
bad question. I'm glad you caught it because I've never caught it, and I've been using that for probably 6, 7 years.
oh, oh,
So you did good.
okay. Well, thank you.
No problem.
But there's a chance that it might show up on the test today or no?
Definitely not be
Oh,
on the
okay.
test. Like I said, it still pops up in the practice tests, but it shouldn't be in
Yeah.
the actual test.
Okay.
Okay. Y'all have your test tonight, right? At like
Yeah.
what's it, 7:30?
Yeah.
Okay. So yeah, ignore that question if it pops up again on the practice test, but you will have it. I've got that reminds me I gotta send Miss Raskovic the actual passcode.
You
She'll
po
she'll text me when she doesn't get it. So
you posted two different practice tests. Which one?
they actually are all good, except what I discovered last night was that the one that I had originally made was actually for the next online test, so it covered more chapters. This one's only going to be up through chapter 25, not through chapter 26.
Because the one that says practice test face to face,
Hmm.
that one had like so much other stuff other than 24 and 25.
Let me double check. Oh, yeah. Well, they're all comprehensive, so they definitely have problems from chapter 17 up. But
Yeah,
the
okay.
the what's supposed to happen is the majority of the questions will be from 24 and 25, and then there will be some hopefully low-hanging fruit, easy questions for chapters 17 through 23.
Okay.
Okay. I noticed that you'd taken it already like 3 or 4 times, so good. That's the more you do it, the better off you'll be.
All right.
This Google Notes or Good Notes or whatever crap I'm using is really aggravating me. Keeps erasing stuff every time I like leave the pencil alone for 2 seconds. We only got about 1 minute before class starts. More there. Ah. All right. Well, I guess it's good enough time to start here. We're actually starting in a new chapter. Last time we completed chapter 26. The good news is this chapter is pretty straightforward and usually can be done pretty quick. I want to make sure, of course, we get through chapters 30 and 31 ideally before by the end of the semester, and I think we're on track to do that pretty well. The most ideal scenario would be me being able to go in and cover the first two, if not three chapters of quantum mechanics, but we might not be able to get there. I see Kara sent me a message. I'm just looking at it real now. Okay, so she asked about bringing extra formulas. No, the formulas that I actually use to put in the actual test are the only ones you're allowed to use. If you happen to remember one, I have no way of knowing it, but if you want one that you're allowed to bring in, it's only those that I put on the board. That being said, remembering them uh ones that aren't really required there is good is being a good student. It normally is a result of you solving a lot of problems, but it's not technically correct. So if I were to ask you to show me your work on a particular problem and then you turn it in and you started with an equation that wasn't on my equation sheet, then I wouldn't be able to give you credit. So that's the negative side. I did just update it. The practice test that I had put out there was only had equation sheets for 21 through 24. I just resubmitted all those practice tests and put in a practice test with equation sheets that actually has the equations all the way up through chapter 25. So it's just a work in progress, but now we got equations from chapters 17 through 25 in the actual practice test, as well as on the actual final you'll be taking tonight. Uh, those of you who are taking it tonight, that is. Thanks for asking that, Kara. That's a good question. Like I said, I completely support you knowing other equations because that gives you a chance to actually see your equation versus what you remember. And if it actually is applicable, that's a good thing. That's a good check mark for you. Starting off with it usually means that you're not understanding enough of the fundamentals to get to the equation that you're using, and that's why I pretty much just stick to the ones that Giancoli has decided to number. So that's the equations that I allow.
I'm so sorry. Where can I find that formula sheet that you just said you updated?
Uh, Actually, here you go. Let me do this for the ease. I just put it in the practice test, so the practice tests weren't showing it originally, but
Yeah,
now
I still don't see it.
it's not even in the practice test
It's
you're
still
looking at
not
now.
showing for me either.
No, that's why I asked about bringing one in originally because I didn't see one in the practice test.
Gotcha. I don't know how long it's going to take to replace because I had to remake one this morning and I put it in this morning as well, but it sometimes takes a little while for it to hit. But let me give you this just so you'll know what's going on. I am there it is, there it is. Sorry, I have to look through my files to find it. GCC stuff. There I am, spring 24. 242. And I think it'll allow me to do this. Let's see. I think it'll allow me to put a picture up. No, it will not let me put a picture up. Wonder if it'll allow me to put in a Word document or a PDF. Let's try this. Nope, it won't let me do that either. Okay, what I'm going to do is I'm going to send you guys a announcement and put it in there. Let's see if it lets me do that. I'm going to choose a file. Yep, it seems to let me do this at least. So, okay, I'm sending out an announcement right now that just says equation sheet and has a bunch of random letters in it because it requires me to put a message. So that's there now. Okay. No, you do not bring your own equation sheet. The equation sheet is built into the final. So when you actually, or excuse me, into the face-to-face test, when you get to the face-to-face test and open it, you can scroll down to the bottom and you'll see that I have copies of the inside, front, and back covers of the textbook, copy of a periodic table, and then top copies of equation sheets. Actually, since you guys are 242, I go ahead and give you 241 as well as 2 pages, which are 242. You won't be able to tell that it's 2 separate pages, but you'll just see it in there with all the equations. But the equation that I just sent you via PDF is the one we'll be using, so hopefully that'll help you guys. Anybody else have any questions? All right, well, we got to get started on chapter 27. I'm going to try to cut it a little short, so maybe I can answer more questions in case you have other questions. Yes, Logan, I did see that you had asked me if you could take it at home like normal. I said yes. I've already set it up for you. You'll just have to open it with the lockdown browser and the Respondus monitor, and your mirror set up like you're supposed to, and that's fine. I think Richard asked to do the same thing, but at the testing center, and that's okay too, Richard, if you'd like. So I'm going to share my screen from my iPad. And like I said, if I finish up early enough, I might actually just take some questions because it helps you to ask them maybe before the test, which supposedly starts about 7:30 tonight. So I want to help as many people as I can. So in chapter 27, it's just called magnetism. And I wrote a few fundamental facts down that are necessary. So the end of a freely suspended magnet that aligns itself closest to north, if you happen to be near the surface of the earth, is called the north pole of a magnet. Now, what do I mean by that? Well, I often do science shows for elementary, kindergarten, middle school kids, even high school kids, stuff of that sort. But I can do it with the lowest, youngest children, kindergarten and stuff. And what we do is we literally just give them like a needle, like literally a sewing needle. Sometimes we blunt the end so they don't jab themselves because, little crackheads. But anyways, then all we have to do is just take and hold that needle and place a magnet near it and just sort of keep running the magnet near it over and over and over again. Because that actual needle is made of steel, it will slowly acquire the magnetic field that you're exposing it to. In fact, if you left it long enough, just laying on the surface of the earth, the magnetic field would cause the Earth's magnetic field would cause it to somewhat align along that needle. Now, then you take that needle and we'll glue it just like a big cork, and then take the cork and rest it in water. And what you'll see, if the cork's not too large compared to the size of the needle and the strength of the magnetic field the needle acquires, the needle will just orient itself such that one end will point roughly north and the other end will point roughly south. The end that points to the north is called the north pole of the magnet. And of course, that means that technically the Earth's north pole is a south pole of a magnet. So when a magnet is cut in two pieces, the result is two complete magnets, each of which have a north pole and a south pole. In principle, you can do that over and over again. Of course, if you get too small, then what will happen is it just becomes no longer magnetic at all. But the deal is you're never going to, and we never have found a north pole by itself or a south pole by itself. And that's consistent with Maxwell's equations. There's a specific equation of Maxwell that looks just like Gauss's law that we studied in chapter 22. Only in Gauss's law, the other side of the equation has the charge density divided by epsilon naught, whereas in the magnetic version of Gauss law, it just has a zero. And if that's zero, that means we will never, ever find a lone north pole or a lone south pole. So far, we've never found one, and we've done a lot of things to try to make them and stuff like that, and it's never worked out. So we, as best we could tell, there are no magnetic monopoles. That's what it's called. So that is a fact of nature that we need to take account of. The third thing that I wanted to mention to you is that Earth has a magnetic field, which obviously case one suggested that, and in this case, the magnetic field actually mimics a bar magnet inside the Earth, but tilted with respect to the Earth's rotational axis. Its strength is about 0.5 Gauss, which is one of the units that we use to measure magnetic field. The modern SI unit is the Tesla, and 1 Tesla is about 10,000 Gauss. So that's gives you an idea basically of how weak the Earth's magnetic field is. But thankfully, we have it, so we could use it to navigate in prehistory as well as in written history. Now, when we actually consider drawing the Earth like a circle like that, you could say, for instance, that this would be the equator. And what we find is that right up here somewhere is roughly where the south end of the bar magnet would be. And that happens to be up in Canada area. And then the North Pole happens to be down here. And not only that, it moves about 10 kilometers per year, the North Pole does. So it's continuing to move. But this is in, actually, your book gave us a fairly specific place for where the magnetic, quote unquote, North Pole, which is actually South Pole, is. It said the North Magnetic Pole, for example, is in the Canadian Arctic. Okay. In the Canadian Arctic. And like I said, it moves from year to year around 10 kilometers, I think, per year. I thought it said that too, but maybe I'm looking at the wrong place. Yeah, about 10 kilometers per year. And moves about 10 kilometers per year. And this is about 1,000 kilometers from actual North Pole. In other words, the magnetic North Pole, which is really a magnetic South Pole, is not that close to the Earth's North Pole. In other words, if you take the rotation axis of the Earth and follow that all the way up till it peeps out of the top of the Earth, the north side of the Earth, you'd have to go 1,000 kilometers away before you'd run into the magnetic North. And that means when you're using a compass, you got to correct for that. Your book was actually kind of cool in that in section 27.1, he shows an old section of a California map where it actually has the north and magnetic north, and it shows that it differs by about 17 degrees. So that's a typical type of map. If you're actually wanting to navigate by, you need to know roughly where the actual north is compared to where the magnetic north is, and that helps you do it. The magnetic field, of course, is not parallel to the surface of the Earth. It actually acts like a bar magnet. So it comes out of the South Pole, or excuse me, comes out of the North Pole and enters the South Pole. What I tell my students is it behaves like retired people. I usually say old people, but I think that might be somewhat offensive, especially as I'm getting closer and closer to what some people term old. So anyways, I say the magnetic field of is basically like old people. They leave the north and enter the south. So the idea being that, of course, a lot of people do retire to Florida. So I think you can follow that enough. But basically what that means is magnetic field lines pierce out of the bar magnet from the north side and then go around and make those cool maps like you saw in the Faraday lab and come back and enter the south pole of the bar magnet. So if we look at our Earth with respect to this, what that means is the magnetic field lines come in the south like this. They actually never stop. They're always complete loops unless they're transitory in nature. And then they poke themselves out of the north end of the magnet and come back around like this. And that's the same thing they do over here. Poking out that way, and there's a angle called the angle of deviation, which is how far it is away from true north, and then there's something else called the angle of dip, and that tells how much lower than horizontal it actually points. The angle of magnetic declination basically varies from 0 degrees to 20 degrees within the continental US. So you can expect it to be off as much as 20 degrees depending on where you're at. And the angle of dip goes from anywhere from 67 degrees in New York to 55 degrees in Miami. The magnetic phenomena was named after certain stones that were found in an area called Magnesia, which is actually in what we call, well, what a lot of people call Anatolia, but basically where Paul, Paul of Tarsus was in Turkey. So Paul from the Christian and Judaic Bible lived in a time and a place in what would have be modern day Turkey now, and roughly that's near Magnesia. And Magnesia is where those stones were found that were shown to attract one another, repel one another, stuff like that. That just happened to be big iron deposits, basically. But the main thing is because it appeared in Magnesia, they called it magnetism. So, any questions on that? So these are just a couple of facts that might come in handy. I did say that the magnetic field B normally has units of the Tesla, named after Nikola Tesla. And of course, the symbol for that is just a capital T. And a Tesla's a big unit again. Typical MRI device, like you might have for to examine an injury or to check out your brain or something like that. They're usually anywhere from 9/10 of a Tesla up to maybe as high as 2 Tesla. Some of the experimental ones we use in physics are 4, 5, 6 Tesla, as far as I know. But generally, the medical ones are around 1.2 Tesla, I think. The best way to make a uniform magnetic field would be sort of like a parallel plate capacitor, where you make a parallel plate capacitor by making a really large plate and you cover it with a uniform charge density. And that one will say be a positive charge density. And you take another plate and make it a negative charge density of about the same magnitude and uniformly distribute it. And then you bring them really close together compared to how large they are. When that happens, you get magnetic field lines that leave the positive charged plate and run into, these are electric field lines, sorry, I said magnetic, that leave the positive charge plate and run into the negative charge plates. And the way we picture electric field lines is that they originate on a positive charge and die or disappear on a negative charge. Magnetic field lines never die or disappear except like transitory when the source of the magnetic field spontaneously disappears. So like if you did something mechanically to make a magnet no longer be a magnet for a split second, there would be a magnetic field existing where the magnet was as a result of the magnet. And then when you broke it, it would slowly fall off. So you might have these little transitory magnetic field lines that exist for a little while. That's why we see so many loops when we see pictures of the sun. The sun's major feature is its magnetic field, in addition to nuclear fusion going on in the core. But it creates these magnetic fields. Those cause the big loops and stuff like that. And normally loops have to be completely closed, again, unless it's transitory. So if you wanted to create a really strong but uniform electric field, you would take and say, okay, let's make a positive plate like this. Sorry, I wanted to make it kind of neat. And let's put that positive plate really close to this other positive plate like this. And this one's actually supposed to be like a little bit closer like that. And let's go ahead and go up to here. Okay. Now, if one of these plates is positive and the other plate is negative, then what we'd see is basically a bunch of positive plates up. hold on a second. Oh, heck, just broke loose. Anyways, get it drawn properly like this. So we get a bunch of positive charges assembled on one side. That'll be our positive charge plate, and then an equal number of negative charges on the other plate, and that's because uh, they're equally uniformly charged but opposite in magnitude, and they're conducting plates. So with conducting plates, that means when you put charges on them, they're free to move, and they're going to move until they equilibrate, which is basically such that each positive charge has exactly one negative charge. So when you got that, now you have an electric field that goes straight from here to here, to here to here, to here to here, to here to here. And again, the idea is that you have a positive charge, electric field comes from it, and then the charge runs into, or the electric field runs into a negative charge and ends. So if you wanted to make a uniform magnetic field, or excuse me, electric field, you would do it with a parallel plate capacitor, and you put the plates as close together as possible, and you stay away from the edges as far away as you possibly can, because as you saw when you mapped the electric field lines for the parallel plate capacitors, it wasn't uncommon for the electric field to do a little crazy thing like that around the edges. So that was an actual issue as well. So again, you want to stay away from the edges, but if you're in the middle of the field, you get a nice uniform electric field. Now let me show you the uniform magnetic field. The uniform magnetic field would best be made by perhaps taking, let's see if I can draw this oval nicely. Okay, that works pretty well. And now I'm going to draw another oval. Now, what I'm going to imagine is this top oval is actually the north pole of a magnet. And this bottom is actually the south pole of a magnet. And as I told you, magnetic fields are like old people. They exit the north and enter the south. And these lines just were really bothersome. I'm sorry. I would like to be a better person and not let that bother me, but that's not who I am. So anyways, what's going to happen here is I'm going to have magnetic field lines coming through the material like this, and then it's going to pierce the surface and then go on through the surface again. So over here near the edges, we are going to get some fraying like we did with the capacitor. But if you stay away from these edges, then and closer to the center, then it's not going to be a problem. But the main thing is with these, you can see that the magnetic field lines continue forever, so that we'll have a bunch of little uniform magnetic field lines in the center, where they're basically leaving the top plate and coming down and hitting the top of the bottom plate. And I say plate, it's just the bottom end of a bar magnet, if you will. But again, all of these magnetic field lines are continuous. So what we look at when we're looking at a bar magnet, for instance, you might say the bar magnet looks like this. And let's say this is the north end of the magnet and this is the south end of the magnet. Then what we mean by that is the magnetic field line, let's say from this line right here, goes all the way through and then comes out this way, loops back around and comes back in this way. What that means is everywhere along that line, the magnetic field points tangentially to that curve. Similarly, there'll be another line right through the middle. And this one is so perfectly aligned through the middle that we don't even get to see it curve. But if we went further away, we could fit all the magnetic field, of course, into the screen. But the main thing is I'm just trying to show you roughly what the magnetic field looks like for a bar magnet, which hopefully you already knew this from your iron filings and stuff that you did in the Faraday lab. Does that make sense? So it turns out ultimately we'll have del dot D, which is something like the electric field, is equal to rho over epsilon naught. That's Gauss's law in differential form. And when we have the exact same equation for magnetism, we use B for the magnetic field. You can also use H, which is what you have when you have a magnetic field inside of a material other than vacuum. So that's another thing they'll use. But in this case, instead of having a rho over epsilon naught or something, this one just has a 0. So this means lines form complete loops. And this one, lines start on positive charges and end on negative charges. Any questions on that? Okay. Well, another neat thing that happens to happen is it turns out that magnetic fields can be created by currents. So for instance, if we had a current carrying wire, say right here, and let's say the current carrying wire goes like this and this, okay, then that's our wire. And let's say that the current I, actually, this is where I want to punch a baby. So the current I is going out this way. Well, it turns out whenever you have a current going through a current carrying wire, through a wire or a conductor or anything, it actually establishes a magnetic field. And the way we specify the direction of the magnetic field when we're looking at a current carrying wire is we imagine that the current carrying wire is in our hand, say. So let's say in this case, this Apple Pencil is a current carrying wire and the point points the direction of the current. What I do is I take my right hand, notice I am right-handed, so I actually have to let go of the pencil I'm drawing with to do this. If you don't and you accidentally use the left hand, you will get the wrong answer. But what I do then is I take my right hand and I grab it so that my thumb points the direction of the current, and then I curl my fingers around. And what I try to do is I imagine my fingers not being these little rigid things that have that straight part and another straight part and another straight part. Let's imagine them like they're clay fingers so that they're always parallel to the outer surface of the pencil. Okay. If that's the case, then you actually get the real direction of the magnetic field. Uh, Otherwise, it would look like, of course, the magnetic field points horizontally here, 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 all those different spaces, and that's not what it does. Okay. So that's one of our right hand rules. You grab the wire with your thumb pointing in the direction of current, then your right fingers curl around the wire in the direction that the magnetic field does. However, the magnetic field lines are smooth and basically are uh, perpendicular to radial. So in other words, they would go the direction of the stripes or the letters on your tires. If you're imagining tires as the model, you could imagine a tire that has a really narrow hole in the center for the rim, and the rim, for instance, is only as big around as this pencil. Then all the tire wording and all that stuff all goes around just like the magnetic field does. So on this drawing, what we can do is I can realize that this current is actually going to go straight down, say, the center of the wire like this. And at each point, I can imagine a plane. So let's imagine a plane right here. And let's imagine that it goes this way as well. Okay. So what I've just made is a plane that is perpendicular to the wire and also therefore perpendicular to the current. Once we have that, then I can give you an idea of what the current, what the magnetic field is doing. So right at this point, for instance, the magnetic field would point that way. At this point, it would point that way. At this point right here, it would point that way. And this point right here, it would point that way. But what it's actually doing is making a complete loop. And we're just choosing little itty bitty dots on that complete loop and drawing them, drawing vectors tangential to it. So here's a magnetic field line. Here's a magnetic field line. Here's a magnetic field line. Here's a magnetic field line, like that. So does that make any sense to you guys? So that is the way it works. As I said, you can imagine the right hand rule. So my wrist comes in, then there's my hand, and then my knuckle, and my other knuckle, and my other knuckle, and then my other knuckle right here. And I'm trying to draw somewhat precisely. So this would be my thumb, for instance. And this would be my fingers curling around. So you can see down there roughly, that's what we're talking about. So you can see hopefully that the fingers are curling around in that counterclockwise way around the wire, and your thumb is pointing in the direction of the current. Okay. Any questions on that? So this magnetic field thing's an odd thing. It should do that. And in fact, your book took the time to draw what happens around a current carrying loop. So instead of just a straight piece of wire, you might even have to consider a wire that's in a loop like this. Okay, so there's a loop of wire. And of course, that could be a loop of wire that's carrying a current I around it this way. So there's our current. And of course, if we used our right hand rule there, what we would see is the magnetic field right here directly under the spot points straight out this way, but it's really looping around like this. And then, of course, going right through the middle of the wire. So it would help for me to erase this little part just so we can realize that that magnetic field line is back behind the wire. Okay. There's also, of course, another magnetic field line for this part. And that's because the current's going there too. And of course, you can see it would also come back like this and point this way for the part of the wire closest to us, which would be this part right here. Okay. So that's ultimately how the magnetic field behaves around a current carrying wire. And you might expect that some sort of weird stuff happens, and it does. It turns out, for instance, that when you have a magnetic field, it can actually impart a force on something. So a magnetic field will apply a force to any charge object that has a non-zero velocity. Okay, so if you have charges moving, then they're going to actually create a or experience a force if it's moving in a magnetic field. And that force, in fact, will be given by F sub B, which means due to magnetic field B. That field is given by this weird cross product, the charge of the object times its velocity crossed with the magnetic field. So hopefully when you took trig, you covered cross products. And when you cover a cross product, you learned a right-hand rule. But if you didn't, that's okay. I'm going to show it to you anyways. So basically what you can do is, again, imagine your right hand like this. Let's imagine, though, that my index finger is pointing one way and that my thumb is attempting to point perpendicular to that. So that's going to be my thumb to some extent. And then perpendicular to both of those is my middle finger. So this is the middle finger. This is the index finger. Okay, and actually I'm going to erase that red line for right now. I'll do a different color in a second. But the main thing we're trying to do here is we're saying that, let me try a different color. I'm going to say this vector right here could be Q times V. Now remember, when you multiply a scalar times a vector, if the scalar is positive, nothing happens to the actual direction of the vector, period. No ifs, ands, or buts about it, right? If it's smaller than 1, you're shrinking the vector. If it's 1 or larger, then the 1 will cause it to not change size at all, but larger than 1 will make it bigger, but it doesn't change the direction at all. However, if the charge is negative, then it flips it 180 degrees. So what you have to do is, when you think about a charge, you first say, well, is it positive or negative? Because if it's positive, then QV is parallel to V. If it's negative, then QV is anti-parallel to V. And then I'm going to take this other finger here and imagine that is my magnetic field B. And then I'm going to say mutually perpendicular to both of those is what my thumb is. And that is the actual force. Okay. So the key thing to notice here is, in principle, if you actually took a cross product of two vectors that were perpendicular to one another, then this is exactly right. But you can, instead of holding your finger, your middle finger like this, that's the special case of when QV and B are perfectly 90-degree angle to each other. But in fact, they can be less than a 90-degree angle, and then it would be more like that. But the main thing is your thumb is still perpendicular to both of those, no matter how that is. So that's a key point. The other key point, of course, you can see right here is this part right here would also be perpendicular to the F vector. Okay. So that's a whole nother rule. And if you want to consider what an actual current carrying wire is, what if I say a current is pointing upward, like that wire I drew on the previous page? Notice the current is going upward in that wire. Are they positive or negative charges that are moving upward? Anybody? Okay. So what we define current to be is what we call conventional current, and conventional current is current that we imagine is being carried by positive particles. So conventional current travels in the direction that positive particles would travel. So what that means is they go from, for instance, if we imagine a battery right here and a wire here and a wire here, then this voltage right here might be, let's say, 12 volts. This voltage right here might be 11.997 volts. And this voltage right here might be 8.00 volts, like that. If that's the case, then what we are assuming is that positive charges are moving that way, and that is in fact the exact same direction as the current I. Does that make sense to everyone? So you can see that if you think about current I as being positive charges moving to the right, that's the same thing as saying QV is going to the right. Now, if we take, let's change colors real quick. Let's say that this right here suggests that the magnetic field in this area is in fact pointing into the page. And that's normally what we do. If we're wanting to talk about something pointing into the page, we do a circle like that. If it's pointing out of the page, then it looks like this. Okay. So if we use our right hand rule, this is a chance for you to actually practice it. Remember, QV, B, F is your thumb. Okay. So I have V, which is the velocity of my particles. Would everybody agree that the velocity of my particles is to the right on the drawing that I have down here with the little charges and the battery and whatnot? So the drawing above suggests a current going to the right. Okay. So that implies V points to the right. It also suggests that the current is due to positive charges. So, which way does QV point? Up, down, left, right, out, or in? In other words, up, down, left, right, out of the page, or in the page. So which direction does QV point in this diagram that I've got drawn? Go ahead, Brandon.
I just had a question about
Oh,
the
okay,
ins
go
and
for it.
outs.
Okay.
Is the top, are they all supposed to be all ins, or is the top supposed to be outs? Like, is this showing like the right hand rule with the thumb pointing to the right, or are they all
No.
going in? Is that like
Oh, that's a good point. No, so this wire is immersed in a magnetic field. We're not thinking at all about the magnetic field caused by the wire. Sorry about that. Yeah, that should have been explained. So let's say this wire is immersed in a B field shown in, whoa, actually shown in green. It completely creates an entirely different magnetic field. In fact, if you wanted to make it a magnetic field that it's creating, it's going to get really weak the further and further you go. But right above the wire, the magnetic field would point out like this. And right below the wire, it would point into the page like this. So you can see why I didn't choose to draw that. Now, Sean had your hand raised too. Sean, is there a different question you had, or did you want to try to answer the question that I just asked? Sean? Oh, he disappeared.
Professor, I just had a quick question. I was solving the practice tests, and I
Uh-huh.
came across a question that I couldn't solve.
Mm-hmm.
It's about two large non-conducting plates of surface area 0.25 meters squared.
Yeah, that
Sharing
was
an
an
equal.
error.
Oh, was it 3.4
Uh,
times 10 to the 7?
no, what it wants for the right answer is like 1.7 times 10 to the 7th joules per square meter, but it's just
Okay,
completely
but do you-
wrong. When I calculated, I get about 5,084 volts per meter, or excuse me, joules per cubic meter. That's actually the right answer. So that question still stays in the practice banks, but luckily Brianna showed it to me, and I checked it and checked it and checked it, and it's just wrong. So it might still appear in the practice test, so ignore it. But just know that that particular one where it says 0.25 square meters and 75 microcoulombs and two non-conducting plates, that question is just wrong.
Okay, so the answer would be 5,084.
Yeah, I got 5,084.375 or something like that.
Awesome, thank you.
No problem. Okay, so back to this. It says drawing above suggests a current going to the right. Therefore, V points to the right. It also suggests that the current is due to positive charges. So which way does QV point? Anybody have an answer for that one?
It should just be to the right, right?
Exactly. So QV is also to the right. So I'm going to circle this. So we know that's there. Okay. And which direction is the magnetic field pointing in?
That should be like into the page.
Exactly. So can you use the right hand rule to tell me which direction the wire should feel a force?
Force is going up.
Okay, let me check that. Sorry, I'm still writing stuff. So yes, when you do QV, which would be to the right, cross B. Basically what you're doing is you've realized QV points to the right, so your hand can do any of this stuff. Notice how my hand moves all these different directions. All those are fair game because all I have to have is QV pointing to the right. But what forces me to lock it down is when my middle finger points the direction of the magnetic field, which happens when I get right here. Now you can see my middle fingers pointing into the page, just like the magnetic field is. So yes, he's right when he says the force is up. So F equals QV cross B points upward. So this is a ongoing thing that you're going to have to learn. So there's a lot of different ways to do these right-hand rules. That's one of them. But the whole reason I did this is because I wanted you to see why another equation happens to also be true. So this equation, F equals QV cross B, is something we need, but there turns out to be yet another equation for when we're dealing with wires. And that one is, I like to write it this way so that we can actually deal with links that are variable and for bits of field that actually can change direction. And what I say is DF is I DL cross B. I think you can see that IDL is like coulombs meters per coulombs meters, excuse me. And then B is just the magnitude of the magnetic field, or just the magnetic field itself. But notice the only difference between IDL and QV is a unit of a second in the bottom. Well, actually, it's not even that, because I is Q over seconds and DL is meters. So we literally get coulombs meters per second for the units for this. So this has units, DL has units of coulombs meters per second. And this has units of coulombs meters per second. So I think you can see, given the fact that conventional current is the direction that positive charges move, then it makes perfect sense that the force on a current carrying wire should be I DL cross B. You really don't have to use it as a differential like I have here, unless the magnetic field varies over different parts of the wire, or the wire direction varies with respect to the magnetic field direction at any part, that sort of thing, which is some of the problems we're going to solve. But the main thing is, these are two definite equations that we can use to calculate stuff. Also remember that A cross B has a magnitude equal to the magnitude of A times the magnitude of B times the sine of the angle between them. And A would be like this vector, say, and B would be like this vector. And if they're tail to tail, that's the angle theta. And what I want you to understand is that A cross B would be in this direction, which, by the way, you can see, hopefully, is perpendicular to both of those vectors. So all of this that's circled or boxed in red or blue is extremely important. Any questions on that? All right, so for instance, next time we'll start up, I'm going to go ahead and let you guys go in a few, but there's a problem, for instance, in example 27.3. I'm going to solve that and some other problems next time, but I do want to give you a little bit of time to ask questions. So I'm going to call that a day. I've given you enough information, I think, to get started on chapter 27, at least the concept stuff. You can start reading, you can start doing the examples. But what I'll do is I'll cover more material next week. I might even make some videos over the weekend. I'm not sure, but when I do those, when I post them in the week's module, make sure you take the time to watch them, especially if they're short ones. But right now, almost everything is all complete lectures, which is obviously, too long. But the deal is we don't want you necessarily watching it in one setting. We want you to dial up to a beginning of an example, watch how that example's worked, and then fast forward to the next example that you're interested in. All right, so we've
Yeah,
got
hi.
15
So,
minutes. So go
quick
ahead.
question.
Go ahead.
Oh, yeah. Okay, great. Thanks. So what about the formula sheet? Did it get posted or are we bringing our own in? That's kind of important. So I
Yes,
need to know.
the equation sheet that you're allowed to use is definitely 100% in the or in the face-to-face exam. So you don't have to bring
It's
anything
just not in
in.
the practice. That's okay.
Yep.
Yeah.
And it
wasn't-
should be in the practice. I don't know how long it's going to take to get there, but it should be. And I just sent it to
Yeah,
you so you
I
can get
understand.
practice using that if you want.
Okay. All right. Thanks.
All right. See you,
That's
Shonda.
all. right.
Anybody have any other questions? You're welcome to ask.
do
Leland,
I
I think it
put
might have
my
been
name?
you. Go ahead, Shonda. What'd you say?
Oh, I'm sorry. I didn't mute. I'm going to print my name.
Oh, okay, gotcha. Yeah,
The
go ahead and
attendance.
type your first and last name into the chat so I know you're here. Leland, you said you sent an email. I think you might be the one I was remembering when I said earlier. I thought it was Richard. But yes, you can actually do that if you'd like. You just have to have a mirror. So I basically what I need, if you're wanting to do this exam at home, you're going to have to take the test that says Logan on the front of it, Logan, because that's the one student that had a 2-hour drive. So I was allowing her to do this. But you need to have a mirror, and it's probably going to be at least as big as a sheet of paper, like 8.5 by 11 size. And what you can do is you can lay your computer like this, say, over to the side. And what I want to be able to do is that camera, when I'm looking through it, I should be able to see a mirror that shows what's on your screen and shows your hands and what they're doing. So if I look anytime during your test and I see you looking over here at something I can't see, I'm going to flag that as a potential cheat and make you come back and take it at a testing center. So you have to have a good mirror set up fairly close so that I can see it through the camera. You might want to test it first by turning on your camera and looking through the camera and see whether or not you can see what your hands are doing, what your keyboard's doing. Basically, I need to see your hands. We've had some issues where people have been doing one, I've seen calculators out during the test. Obviously, I understand that sometimes you need a calculator to log in, but I don't want to see it again once the camera's on. Okay, so if you've got that out, that's going to be an automatic. Okay, you're going to have to retake the test. Okay, and
A
then
calculator?
that it's going to be a different one. Did I say calculator? I'm sorry, I meant a cell
You
phone.
did.
Yes.
Oh,
Yeah, you're definitely allowed a calculator. I'm sorry. Sorry about that. The reason why I sort of make that mistake is sometimes students want to use their calculator in their cell phones. That's not allowed. So you guys have to have your own scientific calculator. I do allow you to use the Windows version that's on your desktop or whatever, and it has the scientific calculator option selected. So if you need to use a calculator, you can use the one on the computer, but only that one. And otherwise you have to use a computer or a actual calculator that's not in your cell phone and not on anything that can access the internet. Okay.
When is the last day we can take the test?
Well, if you're not going to take it at the time you're supposed to, which is if you're in my lab, you're going to take it tomorrow morning at 9. So you're supposed to take it tomorrow morning at 9. If you have a valid excuse that it prevents you from doing it, then I have to make up another test, and you're going to have to take that version of the test at some other date.
Okay. Let me get with you after everybody else leaves then.
No problem. Is this, oh, is that John I was talking to?
Yeah.
Gotcha. Okay, no problem. And that's the deal. So I will make it available for my students tomorrow at 9 a.m. If they're in my lab, I'll give them the password so they can access it. And it'll be due. You actually get a full 2 hours. So it'll be due like 11 p.m. or 11 a.m. or something like that. But you do have to have a password. So your instructor will know the password, and your instructor will also take roll. So if you're not in there and then I see that you complete the test, but you aren't on a roll, then that means that you've cheated or something went wrong. So I have to give you a 0 for that as well. So make sure you don't do that. When we need to be submitted. So like I said, you get 2 hours unless you have a accommodation, and then I, respect your accommodation or whatever. I don't think I have anybody with accommodations. If you do, you're supposed to let me know 48 hours in advance. So do that. But basically you're going to be allowed 2 hours. I can allow you to start a little bit late, but if you start later than like 9:30, then that could actually cause some problems. The deal is basically I don't want anybody to have enough time to complete the test and then talk to you and then you take the test. So 30 to 45 minutes is roughly about as late as you can start it, or else I'm going to have to make up a different test for you specifically. Anybody else have any questions? You can ask subject matter questions too, like that great question that God, I can't remember who asked it now. It might have been Micah, it might have been someone else, but I know Brianna found it. That problem that says 2 non-conducting plates have an area of 0.25 square meters, and one's charged with a positive 75 microcoulombs, the other one's charged with a negative 75 microcoulombs, and they ask you how much energy is stored or what the energy density stored in the electric field is. That question is just screwed up. Throw it out. If you see it, throw it out. It will not be on the test. I made the test, made sure that question wasn't in there. So just know that. Anybody have any other questions? Something you need to see?
Professor, I had one other question. It's when you have two capacitor plates and you
Okay.
double the distance between them, what happens to the potential difference?
Okay, so when you have 2 capacitor plates and you're doubling the distance between them, so what we know is, one, if you keep the battery attached to it, then charge can flow in and out, but the voltage will stay locked down. If you take the battery off of it when it's been charged up, then the charges can't go anywhere, but the voltage can change. The main thing that you glean from that is that the voltage, when you integrate from the negative plate to from the positive plate to the negative plate to get a positive voltage, say, that turns out to be the electric field times the distance. So the voltage is proportional to the separation of the plates.
So if we increase, because the question does not specify whether it stays connected or not.
Okay. Let me try to
so
find
that's why
that
this-
question. Let's see. I can do this pretty quick. This is a capacitor question, I
Yes,
assume.
sir.
Okay, and that would be chapter 24, if memory serves me correctly. And do you know any words of the question? Like the
Yes,
first
a
3 or 4
capacitor
words?
consists of a set of 2 parallel plates of area A
Okay, gotcha.
separated by distance D.
That sounds like it might be a concept question. Does it have any numbers at the top of the question, like in the box that represent like a
No
name?
numbers.
Okay.
This is where it'll say, oh, it quadruples, it doubles, it will like
Yeah, that does sound like
it's one of those.
yeah, that sounds like a concept question. So I'm gonna pull up the concepts and check that real quick. 24, there's my concept questions. Okay, so the voltage between the plates, what did you say it started off as?
A
I see.
capacitor consists of a set of 2 parallel plates.
Yep, of area A separated by a distance D.
Yes.
Okay. The capacitor plates carry charges plus Q and minus Q. If the separation between the plates is doubled, the potential difference between the plates will, in this case, is going to basically double because you know V is equal to the integral of E dot dl. E is equal to sigma over epsilon naught. There's no way for this to actually change. So if you double the plate, that's basically what they're shooting for. I'm trying to see if there's any wiggle room. Yeah, that's about the only way you can do that.
Okay. Because
Yeah,
I was using, my logic was, we know that U is proportional to, like, inversely proportional to the distance between the plates, correct?
right.
So what I was thinking was U would have to half, if I'm not wrong. So then you'd have because you know U is equal to half CV squared.
Okay, got. So you're using capital U, not lowercase u.
Yes.
Okay,
Would
gotcha.
that be like the same correct logic? But I got a different answer, which is I want to know why that's incorrect.
Okay, so you're using 1/2 CV squared. Is that what you used for it?
Yes, sir.
Well, the problem is, remember, yes, the voltage went down, are basically doubled, but at the same time, the capacitance, which was epsilon 0 A over D, that went down as well. So you'd get the same answer if you did it your way, but you'd have to take into account how the capacitance changed and how the voltage changed, not just one of them.
Oh, I see. So if capacitance were to stay constant, then we could use that relation.
Exactly.
Okay, perfect. Thank you.
No problem. That was a good question, by the way. Anybody else? Got 2 John Wilkinsons up here.
Yeah, I'm on my phone
Oh, okay, gotcha.
for the audio and computer for video.
I gotcha. You said you wanted to talk to me later about what you're going to do with the test, or you can private message me, or we can take a breakout room or whatever you'd like to do.
Well, I was just wondering if I could find a way to take the test on Thursday. I'm
Yeah.
really trying to catch up, and I'm really close. I'm like halfway into chapter 25, and I really wanted. I did poorly on the last test, and I wanted to really do good on this test.
Gotcha. And you have lab tonight, supposedly, right?
Yes.
Oh. I'm not really supposed to allow somebody to do that without, like a legitimate reason or whatever, because that's, just giving you an unfair advantage. I will tell you that the chapter 25 stuff is pretty mediocre, pretty straightforward, easy stuff. The 24 is a little harder. Basically, I've got a couple people that have been attending my tomorrow morning, and because they attend that, they get to take the exam then. But they're out of that lab now, so they didn't have any other options. That's the only way I can really allow that, John. I'm sorry. It's just, like I said, it's not fair to let someone else, peak a little bit later and then take it.
Okay. Would I be able to do the at home by tomorrow?
Since you're in that lab, now you're really supposed to take it tonight. I wish I could bend for you. It's just like I said, that wouldn't be fair. If you want to take it with a penalty, I could let you take it tomorrow, or even Thursday or whatever with a penalty. But
Yeah.
it's going to be a penalty associated with it because it's like I said, everybody just supposed to take it at the same time, and
Right.
I'd obviously have to make another one.
Yeah. I'd be willing to do it with a penalty.
Okay.
If that's acceptable.
Yeah, I can do that. I could definitely let you take it with a penalty. I'll have to decide on a penalty. It's probably going to be 5 or 10 points out of 100, not out of how many they're on there. So it would probably be something like that, and I think that would be reasonable. So if you want to do that, just send me an email. I'll mark it, and then I'll set it up. If you want to do it at home, like I said, you have to have a lockdown browser, and you got to have Respondus Monitor running, and then you have to have a mirror that allows me to see your workspace where you're actually working and writing on the pages, as well as the screen of the computer. That's
Okay.
That's the only thing. Okay. Just be careful. Like I said, if I see someone looking down in their lap constantly at an area I can't see, I'm going to have to mark that as suspicious behavior. And I don't want to do that. But it would just mean you have to retake it at a proctoring center or something.
Right. I mean, honestly, I'd rather take it at a proctoring center because
I get
I
you.
just feel more comfortable.
Yeah, it's a pain
Just
in the
with
butt to
my
do
kids.
that. Yeah.
My kids like to come into the bedroom when I'm trying to do
Oh, the
homework,
kids
and
are
I
so
get
helpful
distracted.
when you're taking a test.
It's the absolute worst.
You should get a couple dogs too. That'll work out great.
I have a dog, so
Yeah, it's no
but
problem.
yeah,
I'll work with you guys. Was that Richard and John that both wanted to do that day late or whatever?
But you just said we can take it Thursday.
Yeah, if you want to take it late, because Richard, you're not normally in my lab tomorrow morning. You could take it tomorrow morning for 5 points off or whatever,
At the test
or you
center?
could take it even Thursday at home. But I got to make a whole different test for that.
All right.
So just email me, let me know what you want, and that's fine. If y'all have any more questions, well, heck, there's only 2 of you now. I was just gonna say, if anybody has any more questions, you're welcome to ask.
Yeah, if I have any questions, I'll definitely text you. But I might go to your. Well, hold on. What time is your lab or whatever that you
My
have to
lab is
attend?
tomorrow morning at 9 a.m. And it's JC 20. I think this is JC 26 is the room. And if you have a computer, you can bring it. We also have computers at desktop, but we only have like 12 computers. Usually there's enough students bringing them where we can afford a student to have a desktop computer, but not always. So sometimes that's a little bit of a problem, but we have other rooms we can use.
All right. Yeah. I guess I'll think about it. I'll ask around or whatever. So.
Okay, no problem. Just let me know and do your best to study, and I hope you guys do really well. I am definitely dropping the lowest of the 3 face-to-face exams, not counting the final. The final's got to count fully. So at least take a little bit of solace in that. So if you do really well on this one, you could sort of wipe out the problems that you had from any past test. Not to say that you guys necessarily did. I'm just saying generically. Because, I don't want to tell anybody else's grades.
oh, trust me, I know I did pretty bad last one.
Well, what you told me, it was a lot better than you thought. So, yeah.
Yeah.
All right. Well, you guys good to go? Or you have any more questions?
No,
All
I
right.
think I'm good to go.
If I have any, I'll email you.
All right.
And like I said, I'll email you about when I can do it on Thursday.
No problem. Thanks, John. Appreciate
All
it.
right.
Thanks for sure.
Thank you. All right. Bye.
Have a good day, guys.